Okay, picture this. You are standing deep inside a massive cargo ship, and all around you is the incredible roar of the main engine. We're talking a machine that's multiple stories tall, a true beast of steel and power that's pushing thousands of tons of vessel through the ocean. It is, without a doubt, the most critical piece of equipment on board. But here's the crazy part. The survival of that colossal engine depends on an electrical signal so tiny it's measured in thousandths of an amp. So how on earth can a current weaker than what powers your watch possibly protect a machine the size of a building? To figure that out, we've got to understand the invisible threat it's constantly fighting. So to really get the solution, we first have to get a handle on the problem. And for a huge marine diesel engine, the biggest threat? Well, it's something you can't even see. You see, the lifeblood of this engine is its fuel and its lubricating oil, and both have to be perfectly, spotlessly clean. The real danger starts with something microscopic, tiny, invisible particles of metal or dirt. If those get in, they start a disastrous domino effect. First, they clog the fuel injectors. Then, they cause the bearings to wear out. And the last domino to fall? Catastrophic, and I mean incredibly expensive engine failure. So you've got this invisible enemy. How do you possibly fight it? Well, you build a shield, but not just any shield. This one is smart enough to clean itself. And that shield has a name, the Backflush filter. And honestly, it's a super clever piece of tech. Its main job, of course, is to filter contaminants out of the oil. But the real magic is its second trick. It can automatically reverse the flow. It backflushes to literally blast all the collected junk right off of itself. And that leads to the million-dollar question, right? This filter doesn't have eyes. It's just a metal canister. It can't see when it's dirty. It needs a way to feel when it's getting clogged. So how does it pull that off? The secret isn't about seeing. It's all about pressure. Yeah, instead of seeing, the system is designed to listen. It is constantly listening for changes in the oil pressure as it flows, and believe it or not, that one measurement tells it everything it needs to know. Okay, check this out, because the idea here is actually super simple. On the left, you've got a clean filter. Oil flows in at 5 bar of pressure and comes out at 4.8 bar. It's an easy path, so there's barely any pressure drop. But now look at the right. The filter's all clogged up with gunk, and it's much harder for the oil to get through, so the outlet pressure drops way down, all the way to 3.5 bar. And that difference, that gap between the inlet and the outlet pressure, it has a name. It's called differential pressure. And that, right there, is the magic number. A clean filter has a tiny difference, just 0.2 bar in this case. But a clogged one? Whoa, that creates a big difference, 1.5 bar. This single measurement is the one thing the entire system is looking for. But a pressure reading on its own is just a number. To be useful, it has to be translated into a language that the ship's control system, its brain, can actually understand. And that special language is the 4 to 20 milliamp signal. Now, this isn't some weird one-off thing. It's a huge deal, a universal standard in pretty much all industrial automation. The easiest way to think about it is like a volume knob for data. 4 milliamps is the absolute minimum reading. Think of it as everything's cool. And 20 milliamps is the absolute maximum reading, which means we have a problem. Everything else just falls somewhere in between on that scale. This chart lays it all out perfectly. Look, at 0 bar of differential pressure, a totally clean filter, the signal is right at the bottom, 4 milliamps. But as it starts to get dirty and the pressure difference hits, say, 1 bar, the signal climbs right up to the middle at 12 milliamps. And when it gets fully clogged at 2 bar, bam, the signal maxes out at 20 milliamps. See how it works? It's a perfect sliding scale. So when you see 4 milliamps, just think, A-OK. It's the system giving a big thumbs up, saying everything is flowing great. And 20 milliamps? Well, that's the complete opposite. That is the big red alarm bell. It's the system basically screaming, help, I'm clogged, time to do something now. Okay, so we've got the invisible threat, we've got the pressure sensor, and we've got the secret language. Now, let's put it all together and see this amazing automated system in action. It's this really elegant, hands-off loop. Just follow me here. First, the filter starts getting clogged. That makes the pressure difference go up. The transmitter sees this and bumps its signal up to, let's say, 16 milliamps. The ship's control system is programmed to watch for that number, and as soon as it sees it, bam! It triggers the backflush.
The filter gets blasted clean, all the junk is ejected, and just like that, the pressure difference plummets. The signal drops back down towards 4 milliamps, and the whole system just sits back and relaxes. Until it's needed again.
Now you might be wondering, okay, but why this specific current signal? Why not just use voltage? And that is a great question. The thing is, a ship's engine room is, well, it's electrically chaotic. You have these massive motors, giant generators. It's a mess of electrical noise. A simple voltage signal would get totally scrambled, like trying to hear a whisper during a hurricane. But a current signal, it's tough. It's way more resistant to all that interference, so it stays crystal clear and reliable, even over the really long cable runs you find on a ship. It's just the right tool for a very tough job.
So this whole setup seems pretty perfect, doesn't it? It's automatic, it's reliable, it feels foolproof. But what happens when the signal itself is wrong? What do you do when the very thing that's supposed to protect the engine starts to lie?
All right, put on your engineer hat for a second. You're on watch, and an alarm starts blaring on the control panel. High differential pressure. Your first thought is the obvious one, right? The filter's dirty. Time for a backflush. But a good engineer knows you can never just assume.
Because the truth is, that alarm could be caused by a bunch of different things. Sure, maybe the filter is actually clogged, but what if the sensor's own tiny little tube is blocked, giving a false reading? Or what if the transmitter itself is out of calibration? Or hey, what if it's just a loose wire somewhere in the circuit? All of a sudden, you're not just troubleshooting a filter, you're a detective, and your job is to interrogate the entire system to figure out exactly why the signal is lying.
And that really gets to the heart of it all. This tiny, invisible 4 to 20 milliamp current. It's so much more than just a technical number. It truly is a language. It's like the ship's own nervous system, constantly sending these silent messages about the health of its most vital organ. It's telling a quiet, nonstop story of pressure and protection, making sure that deep down in that noisy engine room, the heart of the ship just keeps on beating.